Greetings and welcome to fourth grade. This week we're going to cover operations and algebraic thinking along with number and operations in base 10. This is quite a lengthy lesson, so be patient. I tried to cover a wide variety of different questions, so there's a lot here. But let's get started with some operations and algebraic thinking. So with operations and algebraic thinking, we're still going to use the four operations: add, subtract, multiply, and divide, identify patterns, and then gain familiarity with factors and multiples. There are two snakes at the zoo, Jewel and Clyde. Jewel was 6 feet and Clyde was 8 feet. A year later, Jewel was 8 feet and Clyde was 10 feet. Which one grew more? Here on a number line, the top represents Jewel and the bottom represents Clyde. We can see that Jewel was 6 feet long if each one of these tick marks represents 1 foot, and Clyde was 8 feet long to start with. So then a year later, they each grew 2 feet. So I tack on the 2 feet here to each one. Additively, they both grew 2 more feet. However, we must compare how long they were before the 2 feet. We would compare what we call multiplicatively. So Jewel grew 2/6 of her length because the 2 feet, if we kind of place it above here, over the 6 feet in its length. However, Clyde only grew 2/8 of his length. So we can see overall that Jewel grew more. We have the following factor pairs of cards. Sort the cards into 4 different categories. Explain your thinking. Take a moment to kind of put them in order, how you think they should be put, and then we'll come back together and see how I did it. I'm going to put them in order based on what they actually multiply to. So 8 times 3 is 24, so I created a 24 category. 3 times 7 is 21, so I created a 21 category. 21 times 1 is also 21, so I can put that card in the 21 category. 12 times 2 is 24, so I'll put that in the 24 category. 13 times 1 will create a new category since that's 13. 6 times 6 is 36, another new category. 4 times 6 is 24, so I'll put that in the 24 category. 12 times 3 is 36, so I'll put that in the 36 category. And 1 times 13 is 13, so I put that in that category. You also could put, depending upon how you did it, you could also arrange these categories in order from smallest to biggest or biggest to smallest. So a whole number is a multiple of its factors. Thinking of factors then, I have 4 gardens in my yard. In my first garden, I have 30 tomatoes. In my second garden, I have 23 cucumbers. My third garden, I have 15 squash. In my fourth garden, I have 19 carrots. What are the possible ways I could arrange the vegetables in each individual garden so that I create a rectangle or square-shaped garden? Take a moment to write down some ideas for each of my gardens. My tomato plants could have the following dimensions: 1 times 30, 2 times 15, 3 times 10, and 5 times 6. I also know that 30 times 1, 15 times 2, 10 times 3, and 6 times 5 are all the same, so I do not need to write them that way or write them twice. For my squash, I could have 1 times 15 or 3 times 5. So 1 row of 15, 3 rows of 5. My cucumbers, though, I could only create 1 row of 23 or 23 rows of 1, which would produce the exact same pattern. Similarly, my carrots, I can only do 1 row of 19 or 19 rows of 1. That's interesting. Prime numbers are whole numbers greater than 1 that have only one set of factor pairs. Composite numbers are whole numbers that have more than one set of factor pairs. So my tomato and squash plants would be considered composite numbers, whereas my cucumber and carrots would be prime numbers. Helen raised $12 for the food bank last year, and she raised 6 times as much money this year. How much money did she raise this year? Sandra raised $15 for the PTA, and Nita raised $45. How many times as much money did Nita raise as compared to Sandra? Louie raised $45 for the animal shelter, which was 3 times as much money as Anthony raised. How much money did Anthony raise? We're going to use tape diagrams to show these relationships individually. So let's start with Helen. Helen raised $12 for the food bank last year, and she raised 6 times as much money this year. How much money did she raise this year? So last year she raised $12. We want to know how much she raised this year, knowing that it was 6 times as much. So I'm going to rewrite 12 6 times, so 6. So altogether, Helen raised $72 this year by adding them all together. Sandra raised $15 for the PTA, and Nita raised $45. How many times as much money did Nita raise as compared to Sandra? So the money that Sandra raised was $15. We know that Nita raised $45 altogether. But how many of those 15 will fit into the total of 45? Well, we would need 3 copies of 15 to reach $45. Therefore, Nita raised 3 times as much money as Sandra. And then Louie. Louie raised $45 for the animal shelter. This was 3 times as much money as Anthony raised. How much money did Anthony raise? We're not sure how much money Anthony raised, but we do know that Louie raised 3 times or 3 copies of how many to get $45. 3 copies of what gives us $45? Well, I know that 15 times 3 is 45. Therefore, Anthony raised $15. Let's make a list of the first 10 multiples of 3. 3, 6, 9, 12, 15, 18, 21, 23, 27, 30. And we did this by skip counting or counting on our fingers. Which of the numbers in our list are also multiples of 6? What pattern do you see in where the multiples of 6 appear in the list? So I rewrote the list and I highlighted the multiples of 6. 6, 12, 18, 24, 27, and 30. I see that every other number is a multiple of 6 within my multiple of 3. Which numbers in the list are multiples of 7? Can you predict when multiples of 7 will appear in the list of multiples of 3? Explain your reasoning. So here's my multiple of 3's again. Again, the 6's are highlighted, and then I super highlighted 21, which is a multiple of 7. The first multiple of 7 appears after the 7th number in the sequence. We might guess that it may happen every 7th number. We could also check by extending our list of multiples of 3 and working our way through them. When looking at the multiplication chart from 1 to 9, which numbers appear only once in the table of products? Where are these numbers located in the table? Why do you suppose that's true? Which numbers appear the most frequently in the table and why? And which numbers between 10 and 20 do not appear in the table? What do these numbers have in common? So I've highlighted the numbers that only happen one time. The numbers are 1, 25, 49, 64, and 81. These numbers only happen one time. These numbers make sense because a number such as 48, which is 6 times 8, which is not on the diagonal, also appears as 8 times 6. This is the commutative property of multiplication, and several of these squares happen. The ones highlighted in this next table represent the most frequently that appear in the table. These are numbers such as 9, 16, 36, which appear 3 times. The numbers which appear 4 times have 2 distinct factorizations into single-digit numbers. For example, 24 equals 4 times 6, which equals 3 times 8. If the table were continued further, other larger numbers such as 72 and 48 would appear way more than 4 times, since the number 72 will eventually appear 12 times and the number 48 will eventually appear 10 times. Which numbers between 10 and 20 do not appear in the table? What do these numbers have in common? So I wrote all the numbers between 10 and 20. And I see the only numbers that do not appear are 11, 13, 17, and 19. These would be considered prime numbers, which means that 1 times 11 is 11, and 11 times 1 is. And I don't see that 11 as an option, 13, 17, or 19. Mrs. Cookie sends cupcakes all over the world. Last month, Mrs. Cookie shipped 525 cupcakes to her customers. This month, she shipped 5 times as many cupcakes as she did last month. How many cupcakes did Mrs. Cookie ship this month? Let's use an area model to represent 525 times 5. Well, I know that 525 can be decomposed into 500 plus 20 plus 5 into its place values. So then I can take 5 times 500, which is 2,500, 5 times 20, which is 100, and 5 times 5, which is 25. Adding them all together, I see that it would be 2,625 cupcakes that she shipped this month. Notice that we decompose the numbers, and then I use the distributive property to share 5 amongst all of them. Another way we could do this is decompose pieces of the numbers. So I know that 5 can be written as 2 plus 3, and I can rewrite 525 as 500 plus 25. Well, then I can create an area model with 3 and 2 on the left and 525 along the top, representing the two numbers that we added together. So then in each box I can fill in 2 times 500 is 1,000, 2 times 25 is 50, 3 times 500 is 1,500, and 3 times 25 is 75. Adding all of these pieces together, 1,000 plus 1,500 plus 50 plus 75 gives me 2,625 cupcakes. We decompose both numbers into more friendly numbers. However, either way, we use the distributive property to multiply the decomposed numbers together. So whether or not we did it just decomposing 525 by itself or both of them, we still get the same result. We can use different strategies to solve the same problem and still get the same answer. Prime and composite numbers are now a new way in which we can classify whole numbers. Sort the numbers into the two categories of prime and composite. Use counters if you need to see equal rows and columns. Take a moment to pause the video and classify the numbers. The only prime number in our list is 2. The others are composite. Some examples, 3 times 9 is 27, 3 times 31 is 93, 2 times 17 is 34, and 7 times 7 is 49. For your homework, watch the Sieve of Eratosthenes located in the Sieve of Eratosthenes homework Dropbox area. Print off the provided worksheet and work through finding all the prime numbers 1 through 100, should be 120, using this ancient technique. Then answer the questions about the sieve on the second page of the worksheet, scan and upload your documents back into the appropriate Dropbox.